Hi. So I'm going to present my undergrad research project that I did with Patrick and Lucy. So the project centered on our ability to detach from external influence. We wanted to ask whether we're able to detach from external information. And if we're not able to, we wanted to look at how things go wrong. So in the real world, we often make decisions under influence. So for example, when we vote, we need to deal with lots of different biased sources of information, and we need to decide which we'd like to listen to and which we'd like to ignore, and it's important that we're able to ignore certain sources of information. There's also plenty of external information that is, or at least should be, irrelevant to our choice of what to do, and it's maybe worth thinking about whether this leaks into our choices. So we will often want to exclude and or detach from biased and unhelpful information. And although there's lots of work on similar ideas, things like priming, we wanted to look at whether we're able to detach from external influence when it's our explicit intention to do so. So the key question that we're asking here is, are we able to detach from external influence? If not, we wanted to look at how we deal with the information that we've tried to ignore. And there are two possibilities here. We could either follow the information, we could adhere to it, or we could go against the information and oppose it. So aside from that, we wanted to look at our subjective experience of our attempt, at least, to detach from external information. And we wanted to ask whether the sense of freedom that we feel over our actions is well calibrated to our ability to detach from information. So towards answering those questions, we had 22 subjects complete a random dot motion discrimination task, where the basic challenge is to decide whether a bunch of dots that are moving on the screen are moving predominantly to the right or to the left. This can be more or less easy depending on the coherence of dot motion. By coherence, I mean the proportion of dots that are moving coherently in one of those two directions against the number of dots that are moving in random directions. Coherence was set for each of our individual participants by a staircase procedure that came before the main experiment. So participants are looking at this random dot motion stimulus, and then partway through presentation, we change the color from white, it's actually white on a black background, to one of these three, green, red, or blue. The color change instructs the participants of how they should respond to dot motion. So there are three possible instructions. First, we could instruct people to adhere to the dots. So if the dots are moving to the right, press the right button. Second, we could instruct participants to oppose dots. So if the dots are moving to the right, press the left button. And third, we could instruct participants to detach from dot motion. So no matter the direction of dot motion, participants are free to decide as they please to press the right or left button. So the key dependent variables that we have here are firstly the proportion of motion congruent responses. This matters because it defines performance in the first two conditions. So in adhere, we want to be making motion congruent responses. In oppose, we want to be making motion incongruent responses. And in detach, this will give us an idea of whether people are actually responding independent of the dot motion or not. Second, to look at how our subjects were making their responses at a finer level of detail, we wanted some measure of the correspondence between participants' responses and motion information. The motion information isn't static, it can change over time depending on the way in which the random dots move. So we wanted to look at that, but I'll get into greater detail about what we did there a bit later on. So these first two measures are all about how people objectively decide what to do, our objective freedom of choice. But we also mentioned that we want to look at our sense of freedom of choice. And towards that, we asked participants to report their subjective sense of freedom of choice. They do this on a scale that ranges from absolute constraint to absolute freedom, and they do this after each action. So this final dependent variable is all about our awareness of how we make our choices. And then we were hoping that we could look at the relationship between subjective and objective freedom of choice. Okay, so moving on to some results, maybe? Oh no, sorry, not quite yet. Okay, so in an effort to track how information was treated before and after people know what to do with it, we also varied the time at which the instruction could occur during the 2.5 seconds of the stimulus. The idea here was that maybe your ability to detach from information depends on whether or not you knew that you were going to want to ignore it when it appeared. This proved to be quite unfruitful. We didn't really gain any insight from this, but we included it and it's in some of the plots, so we did do this. So now on to some results, I believe, yes. So we're looking first here at the proportion of motion congruent responses. So for adhere in green, people want to be making motion congruent responses. They want to be above the chance level of 0.5. And for oppose in red, they want to be down below the chance level of 0.5. They want to be making motion incongruent responses. And they do that. So accuracy for adhere and oppose floats around 60 to 70%. And in both cases, accuracy degrades with later onset. So nothing too groundbreaking here. So if we then look at detach, we find no significant bias away from the chance level of 0.5. So there seems to be, at least from looking at these data, no population level tendency to either adhere or oppose. But it's maybe worth noting that there is quite a large spread here. It's not as though everyone is clustered neatly and closely around the chance level of 0.5. So there isn't all that much of interest to infer from this plot. So people can do the task. They make motion congruent responses when told to adhere, motion incongruent when told to oppose, and they float around chance for detach. And this final point about people floating around chance for detach may seem to be evidence for the ability to detach, but we wanted to analyse that claim a bit more closely. And to do that, we wanted to look at the correspondence between motion information and responses, as I mentioned earlier. So the first task in doing that is to find a useful measure of motion information. So in our efforts to look at how these responses are made at a finer resolution, the first step we took was to extract motion energy from dot coordinates. So we have dot coordinates for 150 frames of the stimulus on each trial. And we can apply spatiotemporal motion filters to these dot coordinates to extract motion energy over time. So we move from a stimulus that looks like this on the left to a time course of motion energy that looks like what you see on the right. So this is an example time course for just one trial, but subjects completed 864. So if we throw all 864 trials on top of one another, we have distributions that look like this. So these 864 time courses define what's really two motion energy distributions, one for rightwards motion energy and one for leftwards motion energy. And these distributions are our starting point for our analysis of the correspondence between responses and motion information. So we have these 22 raw motion energy distributions. These all look a bit different as a function of the coherence that was set by the staircase. So where coherence is greater, the peaks of these distributions move further away from zero, making it easier to tell right from left. So the first step that we took here was to was to flip the sign of the negative distribution, giving us just one grand distribution of motion energy that doesn't care about right from left. We then normalize this to have a mean of 1 and an SD of 1, just to make it easier to compare participants. And finally, we reverse correlated according to response type. So we have two different response types. What we're going to call pro-responses from here onwards are motion congruent responses. So if the dots are moving to the right, you press the right button. If the dots are moving to the left, you press the left button. And what we're going to call anti-responses from here onwards are motion incongruent responses. So if the dots are moving to the right, you press the left. Dots moving to the left, you press the right. So we reverse correlated by response type in order to extract the stimulus parameters that are associated with each of those two response types. And we do this just by splitting the normalized motion energy distribution according to whether individual motion energy samples were associated with a pro or an anti-response. And the idea was then to investigate whether there were deviations in the means from these reverse correlated distributions away from the normalized mean. Why should we expect to find deviations? Well, if you imagine that a subject wants to make a pro-response, then they are most likely to make a pro-response when motion information is strong. And so you would expect the stronger motion energies to be sorted into the pro-response distribution. By that same logic, if a subject wants to make a pro-response, they're most likely to mistakenly make an anti-response when motion information is weak. And so weaker motion energies will be sorted into the anti-response distribution. So if we now look at these means, so we have plotted here the means from those reverse correlated distributions, that we just spoke about. So for each instruction, each subject has two means, one for pro-responses, one for anti-responses. So we have these collection of means. Do they differ? So in adhere, for pro-responses, these are shifted upwards above the normalized mean, as we would expect, because these are correct responses. And if we then look at the incorrect anti-response means, these are mistakes and they're made in response to weaker motion information. So unsurprisingly, the strategy here is to pro-respond. For oppose, we see the same pattern for correct and incorrect responses. So people seem to want to oppose here, which is sensible. So we find, again, that the correct anti-responses are clustered closely together above the normalized mean, and that the incorrect pro-responses are distributed more broadly and they're shifted lower. So unsurprisingly, people make correct responses when there's clear information. So before moving on to showing you the detach data, I think it's useful to just consider what perfect detachment would look like. So if participants were to perfectly detach from the dot motion stimulus, then there's no reason for stronger or weaker motion information to be sorted into the pro or anti-response distributions. And so if we reverse correlate, it should have no effect, and all of the means should be neatly on the normalized mean. So that's not quite what we see. We see distributions that look a bit more like oppose than anything else. So the anti-means are clustered closer together above the normalized mean, and the pro-means are, again, they are distributed more broadly, shifted lower. So this is not significant. It doesn't quite reach 0.05, but it maybe hints at a tendency to want to oppose strong, clear information when we're trying to be free of that information. So although people may be able to detach to a certain extent, it may also be the case that we mistakenly oppose clear information when we want to be free of it. So as a follow-up to this, we wanted to find any treatment of the motion information that was consistent in time. So to do this, we applied regression analyses to predict responses from individual frames of motion energy. And what we're looking for here are individual frames or particular intervals of the motion energy time course that reliably predict responses. So to avoid overfitting here, because we have 150 frames, so we have 150 predictors, we regularized with a lasso. This is just a method of penalizing the inclusion of more parameters. What it does is it runs all possible regression models for all possible numbers of frames included in those models, and it computes success of the models as a function of both model fit and the number of parameters included. So what we care about here is, first, finding the best trade-off between the inclusion of more parameters and therefore increased complexity and predictive power. And second, for the best fitting model defined by that trade-off, we want to look at how many frames are included, where they are, and what the sign is of the weights applied to them. The sign is important because it defines the response strategy. If the sign is positive, then we're just following the sign of the motion energy, so we're adhering to it. If the sign of the weights is negative, then we are flipping the sign of the motion energy and we're going to oppose it. Okay, so just to elaborate quickly on why we did this. So again, if we consider our stimulus and the associated motion energy time course, It may be that particular intervals of motion energy here are of greater interest to our subjects. So you can imagine that there's a primacy or a recency effect, so people care about the start or the end. You could also imagine that information present at the time of instruction is more likely to leak into your choice. So if you think about in the detach case, people need to attend to dot color in order to know that they are to detach on that trial. And so it might be that the process of attending to color allows some motion information to leak through into your response. Okay, so if we look at the responses at the results from these from the lasso procedure, so on the x-axis we have the number of frames included. The number of frames included. Has it gone? No, it hasn't. Oh, I haven't been doing this the whole time. Sorry, I have two computers to deal with. Okay, so on the x-axis we have the number of predictors included in the best fitting model according to the lasso against the sum of all weights plotted on the y-axis. So if the sum of weights is positive, just to repeat myself, the strategy is to adhere. If the sum of all weights is negative, the net strategy is to oppose. So for adhere and oppose here, as expected, the sum of all weights grows with the number of predictors that are included by the best fitting model. Again, this isn't particularly interesting, but it's a nice proof of concept that the analysis does manage to tell these two response types and strategies apart. So again, before moving to detach, it's useful to consider what detachment would look like. So if people were to detach from the motion stimulus, then none of the frames should be informative as to their response, and so all the points should be on the origin. And if there is some general tendency to want to oppose when we try and be independent of information, we should see something that looks a bit like oppose. We don't see any of these two things, so we find no real consistent strategy in time at the population level. Some people seem to want to oppose, some seem to want to adhere, and others just sort of float around zero. So if there is some general tendency to oppose, as we might take from our reverse correlation analyses, it doesn't come from any time-consistent processing of the dot motion information. And this is sensible. So if the tendency is to oppose strong motion signals, then we wouldn't expect that to be consistent in time, because the time at which there is a boost in stimulus clarity is unpredictable. And so people should not have consistent opposition here if that's what we're to infer. So if there is a preference to oppose clear external information when we're trying to be free of it, it's not time dependent. Yes, okay. So moving on now to subjective reports. We're done with all of the objective freedom stuff. So we're going to talk about the distributions of freedom of choice ratings, and I'm showing you them on the scale that participants saw. So on the far left, we have absolute constraint, and subjects saw a message that reads, "My response was determined entirely by what I saw on screen." And then on the far right, you have absolute freedom, where subjects saw a message that reads, "I decided what to do myself, completely independently of what I saw on screen." Okay, so looking just at adhere here, so we split again by pro and anti-responses, we see an effect of errors. So the incorrect anti-responses are further to the right than the correct pro-responses. Not particularly exciting. If you think about what an error means in the context of the two messages that people saw, it kind of makes sense. And if we add on oppose, we see the same effect of errors. The incorrect pro-responses now are shifted further to the right than the correct anti-responses. More interestingly, though, people judge their freedom to be greater in oppose across the board than for adhere. So people feel freer when they oppose than when they adhere, even though both of those two response types are completely instructed. They have no real choice here in either case. If we then add on the detached data, so unsurprisingly, these are all shifted far off to the right, as they should be. But again, more interestingly, subjects report greater freedom when they detach by opposing the dot motion than when they detach by adhering to the dot motion. So it seems that people mistake opposition for freedom when they when they are reflecting on their own independence. And this ties in nicely with the idea that we got from our reverse correlation analysis that showed that maybe people are mistakenly opposing strong information when they mean to be free of it. Okay, so to sum all of that up, we observed a hint of a tendency to oppose when we try to be free. We found no consistent treatment of motion information in time on detached trials, at least in the population. So if we take these 2 points together, people may, in our experiment, be susceptible to influence by boosts in stimulus clarity on detached trials, and this can happen at any time. And so when we try to be free of external influence, strong signals may still be processed and we may have a preference to oppose them. However, people respond to attempts at influence. Consistently, we found that people feel more free when they oppose information that's given to them, whether opposition is instructed or self-generated. So to quickly relate some of this to what we see in the real world and to what we might do going forward. So this conflation of opposition and independence, we see it quite frequently in the real world. So you see teenagers do it all the time. You tell them to do one thing, they will do the other. But if you think that through a bit, it's not quite the same as real freedom. They're just being influenced in the opposite direction to the way in which you would like to influence them. Real freedom would be doing what they wanted, irrespective of what you said at all. We also saw fairly consistently that there was a decently large spread in what people would do when they were told to detach. So we think this could be a sign of an individual preference for adherence or opposition, and that might be something that we will look at going forward. And finally, I think it's interesting to consider whether there's value in being able to detach from external information at all. So you could argue that this is just willfully giving up on information that could be useful. I don't think that's true where the information is unreliable, but more importantly, when we live in a world as we do, where we're constantly under attempts at influence, it's useful to know whether we're able to detach, and if we're not, it's useful to know how we fail. So thank you for your time, and thank you to Lucy and Patrick for the